Okay, so take a moment, take out your bell work packet and your note packet. Feel free to pause the video until you have all your materials. So remember from yesterday we talked that if the base of your exponent, which is this number here, if that number is greater than 1, this would be an example of growth. And if the number is less than 1, it is decay. Well, because b is 1, so our base is 1, this is an example of growth, which tells us that our graph is going to increase. The h value is in our exponent, but we always flip the sign. So h is -1, which is going to move our graph left 1. Our k value is in the back. It's -4, and that's going to move our graph down 4. And lastly, our a value is in front of our base, and because it's greater than 1, it's going to cause our graph to stretch. In yesterday's class, we graphed examples of exponential growth. Today, let's look at some examples of exponential decay. So in your notes, turn to page 5. Again, feel free to pause the video in order to get out your notes. So if the base is greater than 1, it is going to cause our graph to grow, which means it's going to increase. But if we have a base between 0 and 1, that is decay, which causes our graph to decrease. So let's take a moment and graph both. So what we're going to graph is y equals 2 to the power of x, which is going to be growth. And we're going to graph y equals 1/2 to the power of x, which will be decay. So let's start off with our growth graph. So y equals 2 to the power of x. These are our 5 x values. So 2 to the power of -1 is 0.5. Anything to the power of 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. So let's go ahead and graph it. Okay, so we have, and I usually focus on the whole number. So 1 up 2. And then let me zoom in here. 2 up 4, 3 up 8. So remember, we have an asymptote. This graph is going to go straight out here. And that's what our exponential growth is going to look like. And it's growth because if you trace the graph, at the tail end, it's going to go up. So now let's look at y equals 1/2 to the power of x. Now, because it's decay, I'm going to use more values of x that are negative. So what I'm going to use is -3, -2, -1, 0, and 1. Feel free to pause the video and type in your calculator 1/2 to the power of -3, 1/2 to the power of -2, 1/2 to the power of -1, 1/2 to the power of 0, and 1/2 to the first. Now you should have these 5 y values. So let's go ahead and graph our exponential decay on our coordinate plane. So So at -3, we're up 8. At -2, we're at 4. At -1, we're at 2. At 0, we're at 1. And then we also have a point off to the side. And that blue graph represents our exponential decay. Let me go ahead and trace that all the way out. So now let's look at what happens when you compare the two graphs. And if you look at it, it's reflected across the y-axis. It's like the y-axis is a mirror. So what happened was each point reflects across the y-axis. So does this reflection affect our domain and range? And if you look, it doesn't. Because our domain, we still have positive and negative numbers. So our domain is still all real numbers. So that doesn't change. And our range, both of our functions have y values that are only positive. So our range is still, for both, y is greater than 0. All right, so let's go ahead and practice a few transformations. So we're going to go ahead and regraph our parent function for y equals 1 to the 1, y equals 1/2 to the power of x. So let's go ahead and regraph that, and we'll do that one in purple. And let's go ahead and graph it. So at the -3, we're up 8. At -2, we're at 4. At -1, we're up 2. Okay, so we're going to trace that out. And now let's apply our transformations. So because our exponent, we have a -2, that means h is +2, which is going to move it to the right 2. So remember, from our last unit, we always add the h to our x value. So let's add 2 all the way down. So when I do that, when I add 2 to all 5 of these numbers, then we'll have -1, 0, 1, 2, and 3. And now our h value, that number is in the back. And I'm sorry, not our h value. Our k value, that number is in the back. K is 1, and that's going to move it up 1. So we're going to add 1 to all of our y values, coming all the way down. So we have 8 plus 1 is 9, 4 plus 1 is 5, 2 plus 1 is 3, 1 plus 1 is 2, and 1/2 plus 1 is 1.5. So let's go ahead and graph it. But before we do that, let's fill in a few more key characteristics about our parent graph. And we'll do the parent graph in purple. For this function here, which is our parent, y equals 1/2 to the power of x, the domain is all real numbers. And the range is y is greater than 0, and it has a horizontal asymptote at y equals 0. But for our transformation table, the domain, which I'm going to graph that in green, is still all real numbers. But because of our k value, your k value controls two things. Our k value is going to control what our range is and what our horizontal asymptote is. So because our k value is 1, that changes our range to y is greater than 1. And we also have a horizontal asymptote at 1. So what that tells us is that there's an invisible line at 1. I'm going to draw in a dashed line for my transformation. When I draw in my second graph, it cannot go below that red line. So let's go ahead and graph it. I'm going to graph it in green. So at -1, we're at 9. For 0, we are at 5. For 1, we're at +3. For 2, we're at 2. And then from there, it's just going to go straight out, not going below the horizontal asymptote. And that is our example 6. All right, let's look at example 7. So again, I'm going to graph the parent in purple. So let's go ahead and do this function first. And again, feel free. It's just the same table that we just grabbed. Here is the exact same table. So we're just regraphing this table. And let's go ahead and do that. So at -3, we're at 8. At -2, we're at 4. At -1, we're at 2. Okay. And then we go straight out. And for that graph, our domain is all real numbers. Our range is y is greater than 0. And our horizontal asymptote is y equals 0. Feel free to pause the video at any time. So now let's graph our second function here. In our second function, we have an h value of -1, which is going to move our graph to the left 1. We have a k value of -4, which will move our graph down 4. And keep in mind that this k value is going to affect our range and horizontal asymptote for our second function. So I'm actually going to fill in our domain and range for our second function now. So for my second function, the domain is still all real numbers. My range is y is greater than -4. And my horizontal asymptote is at y equals -4. So that means at -4, I'm going to draw my little dashed line in. Our graph cannot go under this line. So we're ready to apply our transformations. So we're going to add the -1 all the way down. And we're going to subtract 4 all the way down. So feel free to pause the video, use your calculator to create your new table, and then check that your answers are a match to my answers. All right, so -4, we're going to go up 4. Let me go ahead and zoom in a little bit so I can see better. And then -3, 0, -2, 2, -1, -3. So from here, if I connect my points, they come down, and then they just go straight out. And that is your graph. All right, take a few moments, pause the video, and copy down our next formula. And this is the formula that we will use for exponential growth. So in this formula, the A value is the ending amount, P is my starting amount, R is my percentage, which is the rate, but we find that by taking the percent and dividing it by 100. T is the time. So, and we use this formula whenever we're growing at a percentage rate. So let's look at this example here. It says the population of Albany, Kentucky is growing at a rate of 2%. So it's growing, so that's an important word. And the rate is 2%. The current population is 2,000. So the first thing we're going to do is write our function rule. So when we write our function rule, we're only substituting in two numbers, P and R. So my function rule will be A equals, now the starting amount, the current is my start. So this is my start, which means this is the P value. So 25,000, and then it's 1 plus, and then to find my rate, take your calculator and take 2 divided by 100. 2 divided by 100 would be 0.02, and that's to the power of t. This is called the function rule. This is what we're going to use in order to answer part B. So for part B, it says, what will the population be in 5 years? So to find that amount, that means that t is 5. So pick up your calculator. I want you to type in 25,000, 1 plus 0.02 to the power of 5. And we're going to round that to the nearest whole number because we're talking about people. So let's go ahead and type that in. So So I have 1.02 to the power of 5. And we're going to multiply that by 25,000, which gave me approximately 27,602 people. And that would be my final answer for part B. Let's do one more question. So now we're talking about deer, and again, it's growing. It's growing at a rate of 3%. So your R value will be 3 divided by 100, which is 0.03. And the current population, that's your starting amount, that's 10,000. So let's write our formula. A equals 10,000, and then it's 1 plus 0.03 to the power of t. So now we're going to use that formula where we know that t is 10 to figure out how many deer will be in the preserve in 10 years. So A equals 10,000, and it's 1 plus 0.03 to the power of 10. And because we're talking about an animal, we're going to again round to the nearest whole number. And that should give you 13,439 deer. Now you should be able to finish all of homework 1. Remember that homework 1 is due on Monday, February 3rd for full credit.